Sound like a man. All right, so the last few days we've been talking about functions and function notation, compositions, and combining our functions, adding and subtracting. So today we're going to kind of look at the thought process of inverse functions and how those work. So how much should you feed your puppy? So calories and food provide essential energy for you as well as your pet. But how much should you be feeding your pet, and how does the size and weight of your pet influence the amount of food they need? So the adult weight of your dog is determined by the number of calories you feed your puppy. The function W equals K over 130, all of that raised to the 4/3 power, relates the number of kilocalories per day, K, to the adult weight of the dog in kilograms, W. All right, so if you feed your puppy 800 kilocalories a day, Sabrina, what will be their predicted adult weight? Yes, so we left out a little word there, yeah. So what will be their predicted adult weight? So what am I going to do for this? Plug it in, yes, and we can use our calculator. So I want to find my W, yes. So I'm going to plug in 800, divide that by 130, and then I'm going to raise that to the 4/3 power. So when I do that, what do I get? 11.28, and we are going to be in what? Kilograms, yes? So kilograms. Okay, so let's talk about something real quick. So the input of this function was what? What was the input for this function? Well, or how about the units? So the input is going to be what? Kilocalories, yes. And then the output is going to be what? Good deal. Is everybody good with that? And that's going to be, the output is going to be the weight of the dog, right? At adult. So the weight is a function of kilocalories fed in life, yes. So what about B? Complete the table to predict the adult weight of your pet with each of the different diet plans, round to the nearest tenth. So if we give 600 kilocalories a day, how much is going to be my weight? And I'm trusting y'all to do the math. So 7.7 kilograms. What about the 800? So 800 was what? 11. Let's round it to 8 or 0.3. Oh yeah, 0.3. It says round to the nearest tenth. I'm not reading correctly. And then 1,000 is going to be what? 15.2 kilograms. Okay. All right. So if you want your dog to weigh 15.2 kilograms, how many calories should you feed him a day? 1,000 calories, yes, or kilocalories, I'm sorry. Okay. So the ideal adult weight for a golden retriever is about 300 kilograms. So how many calories a day should you feed a golden retriever to achieve this ideal weight? So what would I do to find this answer?
You would take the 4/3 and then multiply by 1/3.
Okay, so I'm going to set it equal to that 30, right? Okay, so I'm going to plug in a 30, Pranay. Yeah, I'm going to set this equal to a 30, right? So I'm going to do the inverse operations, right, to solve for this. So what am I going to do to both sides? So I am going to, whoops, Lordy B, raise each power to the what? 3/4? Yeah. 3/4. So the opposite of that, right? So if we had a square, we would take the square root of it. If we had a 1/2 power, we would what? Good deal. Raise it to the second power. Good. All right. So when I raise that 30 to the 3/4 power, I don't know what that is, then what am I going to do? Then I'm going to multiply it by what? 130. Good deal. So what do I get for my K then? I get what? 1 6 1 6 6 6. And we are solving for what? My unit here is what? So we're undoing my original equation, yes? So do you see that? So we are undoing the original equation. Good. All right, the ideal adult weight for a schnauzer is 9 kilograms. How many calories a day should you feed a schnauzer to achieve this ideal weight? So what am I going to do? I'm going to set the equation equal to 9. So only thing that's going to change here is that it's going to be equal to a 9. I'm going to do the same thing, right? So I'm going to do the inverse operations here. So I'm going to raise it to the 3/4 power to get rid of that. And then do what? Multiply by the 130, yeah? So what'd y'all get for K here? 675. Did y'all say 0.5? Is that what I heard? 0.5 kilocalories, yeah? Okay, so how can I write now we've solved two things. So how can I write an equation that outputs the number of calories you should feed a dog whose ideal weight is W kilograms? So what am I going to do here? So I want an actual function or an equation here. So what did I do? So right here, let's look right here. So it's W to the what? 3/4 power. Perfecto. Times a 130. And that's going to give me my what? So this is an inverse function. So this represents an inverse function. So now, what changed about my input and my output here? So what is the input of this function going to be? The kilograms, good deal. So the input of this function now is going to be kilograms, and then the output is going to be what? The kilocalories, right? So what I need to be feeding, okay? So this is our definition of an inverse function, which we notate that with, have y'all ever seen the little negative symbol at the top? So have you ever seen a function that has a little something raised to the negative first power? That is not an exponent, like I just said. It's not an exponent, but that does represent the inverse function. Okay? So explain how you could verify that your equation in question 4 gives you the correct number of calories. What could I do? Do what now? Perfecto. So do the non-inverse function. So I could plug that in. So the number of calories, I could plug that into the what? Original? Yeah. So plug the number. Ooh. Just kidding. Okay, so this is our inverse functions. So something that's interesting about an inverse function is that the composition of the original function and the inverse function is going to give you x. Okay, so so if they are inverse functions of each other, we can show that they are inverse functions by taking the composition. So remember, composition is plugging in one inside of the other. Yes. So I can show that they are inverse functions if this is going to be equal to an x. Okay. So if I take the composition of the two functions, the original function and the inverse function, and it gives me an x, then that is part of the way showing that they are compositions, they're inverses of each other. So I would have to do the opposite way as well. So I will plug the original function into the inverse function, and it should also give me a what? An x. This is going to show that they are inverses of each other. Yeah? Does that make sense? Okay, so to find an inverse, function, you will let f of x be your y, because remember that's what it is, right? So f of x represents your y value. So you're going to let f of x be y. So you're going to replace it. All right. So once you've replaced your function notation and let it be y, you're going to switch your x and y values. So you're then going to switch your x and y values. Okay. You're going to solve the equation for y. So solve this new equation for y. And once you've isolated y, this is, you're going to label it your inverse function. And we label it our inverse function because remember, functions are always functions of x, right? Okay, what else is special about an inverse function? So the inputs and the outputs, what happens with them? They switch. So that means my domain and my range, what? They switch, yes? So in my original function, so I'm going to try to label it kind of crazy. So in my original function, here I have my domain and my range of some random original function. And then now in my inverse function, I have my domain and my range. So they switch to each other, yes? So my range of my original function becomes my domain of my inverse function, yes? The domain of the original function becomes the range of my inverse function. They are switching each other. Tomorrow we're going to talk about graphing these, but graphing inverse functions, they do, I think somebody told me this the other day, we were talking about it, but it shows, it reflects across the x-axis, like so, or y equals x there. So it reflects across the y equals x. Good. Okay, so to prove how to find that the functions are inverses of each other, you have to show both of those, the compositions of f and f of f inverse of x, and you have to show that f inverse of f of x, that both of those things equal an x. Yes? Yes? Okay, are y'all okay about finding an inverse, like setting it up and trying to find an inverse? Okay, so take a second now and work through these 5 questions here. So let's look at number 1. So it says, based on the table, what is G inverse of 12? So how would I find this? So we find the 12 on here, because remember we switch our x and our y values, right? So this is going to be equal then to what? 16. Perfect. All right, so now let's look at this graph for number 2 here. The graph of h is shown, whoopsie, you don't see half of that question down here for number 3. I'm sorry. So it's shown to the right. Find H inverse of 2. So I'm going to look for my y value of 2, right? So my y value of 2 is going to be what? 5. So H inverse of 2 is going to be equal to a 5 since H of 5 is equal to 2. Yes? Does that make sense? Okay. All right, so I want to convert from degrees to Fahrenheit. Okay, so we can use this equation. C equals 5/9 F minus 32. So if I write an inverse function here, what am I going to do? Perfecto. So I'll multiply by 9/5 C. Yeah. And then I will do what to both sides? Add the 32, yeah. So we're just converting Celsius now to degrees. Good? All right, number 4 says the function f of x gives the distance in miles that an ambulance can travel within X minutes of receiving an emergency phone call. Interpret the meaning of f inverse of 26 equals 20 in context. So remember, that's important, in context. Some of y'all have struggled about that. So what does this mean? Okay, so 20 minutes has passed. By the time what? Time the ambulance traveled 26 miles. Good? Okay, perfect. All right, so let's look at now. Here is one where we actually want to find our inverse function. All right, so g of x is equal to 1 over x plus 2. So what did I say that we needed to do? What was the first step? So let my f of x be y, right? So I'm going to change my g of x to what? So I'm going to say y equals 1 over x plus 2. And then what am I going to do next? Switch my variables, yes? So switch the variables. So now your y becomes your what? X. And then your x down there becomes your y. So now what do I want to solve for? So now I want to solve for y. So how do I get y out of that denominator there? So I'm going to multiply by that y plus 2, yes? Good. I need a little bit more space there. So I'm going to have x times y plus 2 is going to be equal to what? So I'm solving for y. So what is going to be the best thing to do now? Divide by x. Awesome. So I'm going to divide by x. And then I will do what? I think I heard it. Minus my 2. So 1 over x minus a 2. So this is my inverse function. So how am I going to label this now? G inverse of the function or the x values, yes? So now how do I use my compositions to verify that they are inverses of each other? Okay. So I'm going to take g of my inverse. And I also have to show that what? G inverse of g of x. Both of those two things have to just give me my variable x. Yes? Okay. So let's look here. So if I plug my inverse into my original function. So here is my inverse function. And I'm going to plug it into my original function. So how am I going to do that? So it's going to be 1 over all of that, yeah? 1 over x minus 2. Plus a 2. Sorry, my brain just went blank for a minute. Good? All right, so what happens with your minus a 2's and their plus a 2? They go away, so I'll be left with 1 over x. And that's going to end up being the x where? In the numerator, yeah? Okay, so far so good. So now if I go the opposite way, so I'm going to plug my g function into my inverse function for x. So it's going to be 1 over x plus 2 minus a 2. So 1 over x plus 2 is technically what? Just x plus 2, right? And what happens to my 2's? They go away, and I am left with a x. Good deal. So that showed that they are technically inverses of each other.